So first off, I'm really excited to do this. It's a very interesting topic for me. I guess the first exposure I had to your work, like this entire thing about blockchain. Blockchain is one of the biggest buzzwords we have right now in our time. And Bitcoin, blockchain, there's a lot of excitement about it. But at least me personally, I know a lot of people don't really understand what it's about and don't understand why there is so much excitement about it. So what's really going on here, and why are people so crazed about this thing right now?
Firstly, hi, Osman. Pleasure to be here on this podcast. Thanks for having me here. I'll get right into it about blockchain. But let me start from how I got into blockchain, and maybe that will give a sense of what I find interesting in it. What are the exciting technological breakthroughs that have actually happened to make blockchain possible? So 2 years back, when Bitcoin was at its all-time high and everything, people were talking about blockchain. I think for many people, the introduction to blockchain really comes when people talk about Bitcoin and its price and, how somebody became a millionaire or a billionaire or whatever. And the obvious answer to that, that many people give is, well, it's a bubble and it's going to burst and all that. And here I'm not going to take a position either way. It may be a bubble, it may burst, it may have value, and it may stay. And as you can imagine, this is not investment advice or anything like that. But I think there is something more foundational going on with blockchain. And that's really what excited me, not the price movements and stuff. Okay, so what is going on in blockchain, which is really makes something possible that was never possible before? And this is what the way I would phrase it is, it's possible now to do computing in the absence of intermediaries. So think of when you log into your Facebook, right? You're sending some information, you're typing in your login, you say, oh yeah, I want to look at my friend's profile. Then a request goes to the Facebook server, right? Facebook has servers all around the world, and the server is going to respond to you and say, hey, this is the login, so it's a valid user, he or she can access this other person's information, and then you get it. And it's the same thing when you access your bank account, right? So you log into your bank account, the server, the Bank of America or whatever bank you're using, has a server at the back end, and the server is going to tell you if this is the amount of money remaining. And if you look at a lot of modern economy, it is basically run by computational intermediaries. What do I mean by computational intermediary? I want to talk to you, right? I'm on Facebook because I want to talk to you. I'm on Zoom because I want to talk to you. Right? But the only way that it's being enabled is it all gets routed or intermediated by some server in the middle, right? Run by somebody, which provides security, provides aggregation. For example, think of Uber. Uber provides aggregation of traffic information, of rider information, of where taxis are, and so on, and connects the information together. Right? So that's what the role of these intermediaries are. They provide trust. They also provide market aggregation. Whereas your local taxi operator only had information about the 10 taxis that they were running, Uber has access to 1 million of them. So that's the scale difference that makes Uber way more efficient than your regular taxi. Okay, so I think of these phenomena as computational intermediaries. I want to do some computation involving other users, right? So I have a phone, the taxi guy has a phone. This is really just the two of us should be talking to each other. But Uber sits in the middle and provides some trusted layer. For example, it gives me driver ratings, it gives me user ratings. And these are critical information before you jump onto a random person's car. And so the trusted intermediary is providing you some information about the previous behaviors, right, in this case, stored in a trusted ledger. A ledger is just anything that's a storehouse of information, which tamper-proof. And if you think about it, all of these intermediaries like Facebook, Uber, eBay, Amazon, YouTube, Zoom that we're talking over, all of these are essentially computational intermediaries. And in some sense, the modern economy is really run by these computational intermediaries. And they have provided us with huge efficiency gains that were not possible without this scale of aggregation. But the loss that we have is the centralization of both information and power. For example, Facebook dictates what kind of filtering algorithms go before I view whatever I want to view. Uber takes 25% or 20% or whatever their current incentive scheme is of the taxi fee that somebody is paying somebody else in Africa.
So you're saying that, sorry to interrupt here, but
please make it attractive.
So if I'm understanding this correctly, you're saying that this intermediary or this kind of platform for holding data or whatever, right now is in a state where it's held by kind of just one agent, right? Like just it's all in one spot. They have total control over the entire thing. That's kind of the main idea here.
That indeed, that's exactly what I'm getting at. And even though the end goal is not that intermediary, the end goal is matching between the rider and the taxi driver, or it is between connecting you and me. And it's not really about the intermediary. The intermediary is just there for providing this efficiency gain. Right? So, for example, Zoom runs servers all around the world, and that's what gives us this low latency interaction that we're having here. And it's similar in all of these different problems that there is an intermediary, and the intermediary's main benefit is efficiency and aggregation. So that's how the current economy is run. And if you look at it, is it the best way, right? And what happens in the lifetime of these intermediaries is initially when there is a growth spurt, when Facebook is acquiring more and more users, or when Google is growing and they're able to double the number of users every so many months, then they're not so eager or they're not so worried about their monetization models. However, once they've hit the saturation point, then they're scrambling to figure out, because as a company they have to grow in revenue. They can't grow by acquiring more users. They can only grow by monetizing the existing user base.
Right.
And so that leads this intermediaries to have this interesting phenomenon where initially all of them play good. And then over time, it just becomes more and more difficult for them to keep maintaining that model business-wise. Mm-hmm. So if there is an alternative model, which does not require these intermediaries, but gives you the efficiency gain, then you have a completely different universe.
Okay, so this is kind of just like it's an efficiency problem. The current thing, this idea of the intermediary is just a means to an end, but it's not necessarily the best means to that end.
That's right. That's exactly right. So you want the efficiency gain that comes from having these good intermediaries, but you don't want the centralization of data and power that goes along with it, right? Because you don't want to also go back to a universe where the only way you can get your taxi is there are like 20 or 10 taxi companies in your neighborhood and you have to choose one of them, and they're not efficient because they only have 10 taxis each and so on. So there is an efficiency gain that comes from this aggregation, and you want that because that has made our lives definitely more efficient. But is it possible to get these efficiency gains without the collateral damage of giving up power and information? So that's a key question, I think.
Yeah, so when you're talking about this entire like centralization, so is it the same idea as like having these data centers with, all these big computation centers that, I don't know, I guess we hear about taking up space and power and stuff like that. Is that kind of the same thing going on here?
It is true. So now that if you look at, I want to run something like Facebook,
yeah,
then I need to run a massive cloud with, so many different servers and so on. But what we need to understand is sometimes, running it at scale gives you an economy of scale, right? So they can update software more easily, they can update hardware more easily, they can do fail safes more easily. So there is a certain benefit of efficiency that comes from running all the computers in the world at one place rather than at different places. But is the collateral that we're willing to pay that all of our information and power, especially, is being centralized? I think that is what, to me, the blockchain offers an alternative possibility. And that's one of the most exciting reasons that I really got into it.
So that's why people think of it as secure, right? I guess it's like having your eggs in many baskets instead of one basket. At least that's kind of the intuition that's coming to me now.
That's correct. So instead of having, so the way, we will get into how the blockchain solves this problem, and we'll really talk about the issue that you're raising here. At a high level, the way I think about it is, instead of having one intermediary, if you have many intermediaries which are competing with each other, and none of which have a fixed position. So because their position can be removed always by competition. Then you have a much more effective intermediary system. So that's really what the blockchain offers. If you go deep into it, even though at a high level people say it removes the intermediary, right? Yeah. But you do need somebody to offer that computation and somebody to offer that storage or somebody to offer that efficiency gain. So I think one way of thinking about it is it removes a single entrenched intermediary and converts it into a market where many, many intermediaries are competing with each other to serve. And the incentives are designed in such a way that even if you don't want to serve me, somebody else would want to serve me at a lower rate, and as long as it's economically feasible for them to do it. So that incentive and market mechanism that goes underneath the blockchain is really responsible for the idea that essentially it has removed the intermediary.
And so the excitement is that this is kind of, this concept or this idea is underlying so much of what is big in the modern world, like Facebook, Google, all these different kinds of technology that we're having now. So the excitement is coming from the fact that this is applicable to all these different types of things and can change all of them.
Indeed. So therefore, the point I'm trying to make is that blockchain is not restricted to cryptocurrencies. Cryptocurrency is one application, because that's an application where you're just thinking of either a payment system or a store of value. And normally, if you want to run a payment system, you need to run a server, right? So somebody runs a server which says, hey, Osman has this much money, John has this much money, Sreeram has this much money, and so on. And when I make a transaction, it goes and it adds an entry into the ledger saying, Sreeram gave Honda this much money, right? So that's how a payment system is run currently. There is a server, and the server stores the information about who has sent how much to somebody else. That's how a Visa is run, or a PayPal is run, or Square is run. So the main thing that blockchain enabled in payments is, if you didn't have blockchain, right, you could say, oh yeah, okay, each dollar, let's say, comes with a certain password. And if you have that password, which means you have the rights to that dollar. This may be a simple initial idea. And the reason this idea fails is, suppose I gave you the password, right? So suppose I want to transfer money to you. So I gave you the password. If I give you the password, does it mean that I have forgotten the password? You can't say, right? Like, maybe I still have the copy of the password. Maybe I have also shared this password with 2 other people, not just you. So how do you know that you're the unique owner of this password or of this token? And this was only possible when there is a central registry which was maintaining this information. Really, what the blockchain offered is a mechanism for a distributed or a decentralized storehouse of this set of transactions, and where you can go and say, hey, this coin is currently being held by A or B, and you can verify that, and in a manner that is secure.
I see. Okay, so I guess what I'm taking away from this right now is that Um, it's a matter of dealing with these kind of scalable problems efficiently, and also a matter of security as well. That's kind of where the security aspect comes of it. And I guess maybe that's what it is about cryptocurrency that people are saying, um, that this kind of approach is a lot more secure in that sense. If not everything is in one spot, it's harder to get that information if you're an attacker. Uh, so okay, that's interesting. And I guess okay, that's I guess a pretty key point that it's not just about cryptocurrency. Blockchain is kind of in everything. So that sort of explains where that entire excitement is. So okay, so I mean, given all of that, what you spoke about in your talk is, or in I guess one of your most recent pieces of work is the blockchain trilemma, as you've called it. What exactly is this problem, and how did you come to find? How did you come to be solving this problem?
Yeah, it's so while these these aspects that my interest in Trilemma or even just in blockchain, I'll explain in three ways. One, I just went through, which is mostly a market and an economy and an incentive logic, which is saying that, having single entrenched intermediaries is worse than having distributed competing intermediaries. And so that's one of my interests in blockchain. My other so I have two more reasons why I came to blockchain. The second one is a more philosophical reason, and um, and it really comes from my background, or I'd say dabbling in evolutionary biology. And there is a beautiful book by Yuval Noah Harari that some of you may have read. It's called *Sapiens*. It's a recent book, and it's very illuminating. And in the book, he makes a case for why humans have one species, Homo sapiens, have come to dominate this planet to the extent that this one species can basically determine if any other particular species will continue to exist or not. It's really a kind of unprecedented point in evolution. And he asked this question, why is it, how is it that it has come to be that this is where we are? What is it that's so special about the species? And while an initial reaction may be that, well, humans have brains, they can think more, in a much more advanced manner, and so on. But really, if you just drill down to that, it's not entirely the sole reason, because if you take a single human, as smart as they may be, and put them in an island with a gorilla, we all know how that's going to end up.
Yeah.
So the intelligence only plays a role in survival insofar as it can cooperate with other individuals having that similar intelligence. Right. So the thesis that he comes up with, which is really fascinating, is that Homo sapiens have come to dominate this planet because it is the species that can cooperate flexibly in large numbers. Three keywords here: cooperate. Right? We humans, if you took the same analogy, if you took 100 gorillas and 100 humans, already you will start to see that the dynamics will start to shift in favor of humans, because they can cooperate. They will create complex structures, many things that other animals are not necessarily capable of. So they cooperate in large numbers. We cooperate in large numbers because, for example, to put a man on the moon, right, we have to build a rocket. And no one person is capable of building a rocket. And it's really out of cooperation of hundreds of thousands or millions of people that we come to build a rocket, or have a MacBook, or any of the other amazing things that we really take for granted today. And so he says cooperate in large numbers. But then he points out that it's not only humans that cooperate in large numbers. Army ants, for example, cooperate in large numbers. So humans are unique because they cooperate in large numbers flexibly, cooperate flexibly in large numbers. What do you mean by flexible is the cooperation is not mediated by genetics. The cooperation is mediated by societal rules that we can adapt at the speed of thought. For an army ant cooperation to emerge, it takes genetic timescale, evolutionary timescale, to really for them to adapt to a new structure. But humans, we can reorganize ourselves in an instant. And so it may seem to you that all of this has no relevance to blockchain. And the reason I think it is indeed relevant is any mechanism that enables us to cooperate flexibly in large numbers provides the species an evolutionary advantage, not just, an economic or an individual incentive. So, and I really think blockchain is a mechanism for cooperating flexibly in large numbers efficiently. So,
cooperating in large numbers. That's a really fascinating idea, and I can kind of see how that is underlying so much of the stuff we have, even in the modern world. Stuff like why the internet became such an advantage is kind of that same kind of concept. So I guess I begin to see how that's underlying everything, and what a powerful thing that is, right?
Yeah, indeed, right? If you think about the evolution of just Homo sapiens over time, initial cooperation was tribal. So you have your tribe, you have 100 or like a small number of such people, and you know everybody, right? But you can't retain more than so many people in your brain and understand and maintain their state in your brain. And so you can cooperate with 100, 150 people, and already that gives you a small evolutionary advantage over other species. But then over time, the only way, if that was the only level of cooperation that we could achieve, we would never be able to put a man on the moon or, think of going to Mars or whatever else that we're taking for granted today, or build the internet. So the next step, I would say, in cooperation came with institutional cooperation. Institutions like religions, like countries, like companies, basically created frameworks where individuals can cooperate at much larger scales without having to know each other, because they're all part of this hierarchical structure. You only need to know somebody on, local to your hierarchy, and the hierarchy intermediates the cooperation in such a way that everybody can then agree on what things they need to do in order to get to that common goal. So religions, countries, institutions, laws, all of these things helped create these hierarchically intermediated organizations, which has enabled our cooperation at large scale to today.
This is kind of underlying almost every great thing mankind has ever achieved, this idea of being able to cooperate in these numbers flexibly. It's come through with, pretty much everything, right? From technology to society, to art, to whatever it is that makes, all these things that we've created amazing. It seems to come down to this idea. So if you can leverage this idea, then that can, I guess, lead to true advantages, truly powerful advantages.
Indeed. And only when I really hit upon this thinking did I have a kind of fundamental resonance with this blockchain.
Yeah.
Because I think if a cooperation structure can give a fundamental advantage for humans to better cooperate with each other, because what is really preventing cooperation? So if you to see why blockchain provides an advantage, you need to really think what prevents or what is the friction for cooperation. And the basic friction for cooperation is trust. Am I going to cooperate with you if I'm not sure that the reward is going to be equitably distributed between us? I won't. I'll only cooperate with you if I somehow understand that the reward is going to be equitably distributed. And that is really the fundamental thing assured by a blockchain, is that cooperation. So we all cooperate, for example, in maintaining this blockchain or maintaining a ledger. And we know that the reward and the incentive scheme has been designed such that the total upside or whatever the gain that accrues is divided equitably in a certain way, because you own a certain number of Bitcoins and those coins are going to grow in value, or you own ethers or whatever else the system may be. But when you drill down to it, what it really is a mechanism for equitable, which guarantees equitable sharing of rewards as long as certain technical conditions are met. And that really is a very powerful force in removing the trust frictions that have impeded cooperation. But I want to make a small point here. The cooperation that I'm talking about that's enabled by blockchain is only what I'll call as digital cooperation. If you want to cooperate, for example, to till a land, right? No blockchain can assure you that you're tilling as much as your friend or whatever.
Yeah.
So it's only in the realm of purely digital cooperation, which as I pointed out, all these examples already are mostly digital intermediaries. For example, Uber. When did you last talk to somebody at Uber? You don't have to, because it's more or less an incentive system and rewards and points and all of this that automatically equilibrate to the correct circumstances. And only in the rare instance when this fails, you have to make that call, which most Uber riders never do in their entire life. So it's really a purely digital intermediary. And only when we're talking about purely digital intermediaries does this framework of transformation, which is using blockchains, can really play.
I see. Okay. So I guess that leads us to the problem that you guys started addressing with the entire.
Oh, yeah, the trilemma. Yeah. I'll come to the trilemma. So that I give two reasons why I got interested in blockchain: the economic, philosophical. The third one is technical, which is really the trilemma. And the third reason is, okay, all of this is great and fascinating, and blockchain is going to be a big advance, but we always have to ask, what is it that I can do or we can do about it? And that's really where the technical interest for us came by. So it's also a context for me to dive a little bit into my personal, background or technical background. I did my PhD at University of Illinois Urbana-Champaign, working on a field called information theory. Information theory is traditionally it's a department it's a subset of electrical, computer science, statistics. It's an interdisciplinary field overlapping all these different areas, and it was really pioneered by a single person, Claude Shannon, in a breakthrough paper in 1948. And what it really did is systematize what we mean by information. How can you compress information? How can you transmit information? How can you process information? What are the fundamental laws governing information? This is really what was laid out in this field called information theory. And I would say, along with Alan Turing, Claude Shannon really pioneered the information age that we really live in. The understanding that almost all of information can be represented by bits. How should you store bits? How do you communicate bits? How do you process these bits? And the fundamental underlying mathematical laws governing them were all really set in motion by Claude Shannon in this field. This field, attracted me right after around the time I finished my undergraduate study. And from that time on, I've been basically, interested in information theory. And the reason actually Claude Shannon was studying this is understanding how to communicate efficiently. So this was this was a time, we're talking about 1940s here, a time at which broadcast television had just the possibility of broadcast television, broadcast radio, telegraph, all these things were just being brought in. And so he was thinking about what is the unifying thread underlying all of these disparate systems. What are optimal ways in which one can encode information such that even when corrupted by the noise that any information is nominally subject to, you can still reconstruct the transmitted information accurately. And he was thinking about all these questions, and he was really way ahead of his times. He proposed mathematical laws whose fusion really took 60 years for us to realize. Inventing those particular communication algorithms that he postulated, it took several decades before they could actually come into reality. And in my doctoral study, I was really looking at applications of information theory to communication networks. When we try to build new communication networks, which we can call as ad hoc networks, networks, right? Networks without fixed infrastructure. If you look at wireless, either Wi-Fi or cellular and so on, they're all infrastructure-based technologies. You have a computer and then you have a base station and you communicate. For example, from your cell phone to the base station in a cellular system, or you communicate from your computer to a Wi-Fi access point. The Wi-Fi access points are all connected through some wireline network or whatever. Mm-hmm. So ad hoc networks is a different philosophy which says that we don't necessarily need any intermediating infrastructure. You can directly communicate and form networks where I send information to my neighbor and the neighbor forwards it to my other neighbor and so on, and together we can create large-scale networks. So my PhD thesis was really in this area and trying to understand some mathematical problems in this. Mm-hmm. And right after that, so we did all this mathematical work, but it did not have a direct impact or application at that time. So what I ended up doing was I went to Berkeley to do a postdoctoral research, and I was looking for other areas where I can apply the same methodology and mathematical thinking, but to something that's more readily applicable. And I came upon computational biology, which was something I've been working on since that time. And however, what happened was in 2 years back when I got introduced to blockchain, and I was looking at what are the basic reasons why, even though blockchain has the potential and promise that I just laid out over the last few minutes, why is it that it hasn't seen these applications actually proliferate?
Right. I guess that's the question for a lot of us right now, right? Like, we've been hearing about blockchain for the past several years, but it seems like predominantly right now it's a cryptocurrency thing. And
that's right.
Like everything that you talked about, all these different types of things, it was kind of news to me, even though I'd heard about it vaguely, blockchain entering other things. But it doesn't seem like, it seemed more like it was like an idea and not something that was actually happening.
That is indeed true. That is indeed true. In fact, that was exactly my assessment 2 years back when I was just looking at it. It seemed like, all these people claiming that they will build an Amazon on blockchain or they're going to build a social network on blockchain. Then I look at it and the technology is so rickety that it's not possible really to build something at that scale, right? So if you think about Amazon may be doing billions of transactions per second, including its EC2. And whereas blockchain was capable of delivering 10 or 20 transactions per second. So if you just look at the underlying fundamental technology of blockchain, right? So you think of the underlying rails, right? That limits the speed at which everything in the system can run. And in blockchain, it is this thing called consensus. Consensus is just, because you have all these distributed entities doing different things, they all have to come to agreement. And the rate at which they can come to agreement is going to limit the rate at which you can deliver any application. And in Bitcoin, the two fundamental limiting things were throughput, which is how many transactions per second can you process in this system. That's like 10 transactions per second. And how long does it take for a given transaction to go through or get finalized? That is a couple of hours. And these are not numbers that are going to enable social networks or Amazon to be or Uber to be built on a blockchain. So you really need to improve these underlying rails to actually enable this new class of applications. And then that's when I got interested from a technical perspective. So that's the third reason I got in, is these are really the two things that a communication network designer always talks about. What is the throughput of the communication network and what is the latency, right? So if you look at Verizon, they're going to advertise and say, hey, we do 40 Mbps, or your Comcast is going to tell you we give you 200 Mbps. They always talk about throughput. And also about latency. You go to speed test and then you check how fast your computer is. The two things you see: how fast is it downloading and how long does it take for a ping to return. And says, 20 milliseconds. That seems reasonable.
Yeah.
So we're talking about ping times of 20 milliseconds on your speed test, but we're talking about 2 hours in your blockchain, you're kind of out of orders of magnitude here. So it needs new technology to be developed that can actually close the gap between what the current state of the art is and where the potential lies. And this really fascinated me because in communications, the tech, if you just look at the communication industry, it has become so efficient that any improvement is very difficult. The improvement comes from people allocating more spectrum or more bandwidth or laying new fiber and so on, not from improving the technology or the algorithms. That is a small component of the improvement. A large component of the improvement comes from allocating spectrum.
Mm-hmm.
Whereas here is a technology that seems to have a huge difference between what is fundamentally possible and where it is at today. And that kind of lit me up as a kind of a communication person, saying, hey, how do we really design these systems that can have very high throughput and low latency? Or maybe there is some fundamental mathematical law prohibiting such an agreement at such a speed because things are distributed. Can we either uncover those laws or design new systems that can actually achieve the optimal speeds? So that's where my technical interest.
Right. Yeah. So I want to touch on that point a little bit. It seemed like a very insightful kind of thing. So what happened is that your kind of background that you had, the knowledge that you developed through your doctoral studies, you were able to find a way to apply that. It was at a level that was fundamental that you were able to apply that to several different things. And I guess your research tells that trend because you have blockchain systems, deep learning, information measures estimators, computational biology, wireless networks. So I guess like as a student, what I'm taking away from this is that you're taking some fundamental piece that you learned and seeing where it can be applied, and then the opportunity you identified in blockchain was that you found something that was far from what is fundamental. You found a big gap between the current state of the art and what is fundamentally possible, based
Exactly.
on what your communication theory background was, and I guess you were able to bring that over to something that maybe hadn't been seen in the field as much. Is that right?
Exactly. That's indeed perfectly put.
Right.
The thing is, with blockchain, many people from different backgrounds are really needed to build a completely new ecosystem. And what had happened was from the academic fields, people from certain areas had already started looking at blockchain in a more kind of fundamental way. What are the underlying principles? And the first people, as you may expect, to come into blockchain is cryptographers, because blockchain has security, so digital signatures, hashes, all these things, and they have built an amazing infrastructure of new methodologies. For example, the idea of what is called a zero knowledge proof. A zero knowledge proof is a simplest way to explain it is, for example, let's say I have a password, and you want to know that I have a password, but I don't want to tell you my password. Okay. But you want to know that I have a valid password. Maybe you have a list of passwords. I don't want to tell you which password that I have. But you want to know that I have one of the valid passwords. So it seems like a kind of no man's land, right? Like there's no way to do it.
Yeah.
But really there is in cryptography. And these are really amazing techniques called zero knowledge proofs, where you learn nothing about the particular password that I have, except the fact that I have a valid password. So, and you can imagine immediately that, for example, when I want to make a transaction, I don't show you which coin I own, but I show you that it is a valid coin, and in a zero knowledge way. So these can add really a very strong layer of privacy on top of blockchains. And these were things that academic cryptographers really brought into this space. And similarly, distributed computing people brought in better measures of security, how to do different things. And I think there is a large role for people from networking and information theory, from kind of my own background, to look at it
from a different angle. You were able to see what prior researchers hadn't been able to see because they were kind of looking at the problem from a different angle entirely.
Yeah, exactly. And it is always true in a kind of a new and upcoming field that you require very, very different angles. For example, somebody from economics may think of a blockchain as an economic game and understand incentives and equilibrium, and when will somebody not do this. And somebody from law will think about is blockchain really a company or is it not a company, and when can you file an antitrust law against a blockchain. These are very different angles, and all of these are required. A diverse set of thought is required to really take any technology to its fruition. And it was, I would say, a fortuitous for us to have run into blockchain at a place where really ideas from networking, information, and coding theory, which were really our expertise, could make a
So in solving these problems that you talked about, these fundamental problems of like throughput, latency, these differences, what was the process like? How did you go about solving that problem?
I would say most of this is very similar to how any research is done, but this can provide a kind of a perspective on how we did it. So one thing that I really like is I like wide range collaboration. I work with many different people from our university, my own graduate students, faculty at other universities, talk to them, discuss. So there are, I would say, two types of researchers, more or less. And one is a kind of a hermit type thinking. I take something, go into my room, sit down, and I just come up with something. And that's
the
one kind of...
in the movies, right? Like writing on the walls and...
yeah, exactly.
Yeah.
Exactly. So, like Goodwill Hunting or whatever.
Yeah.
That's one kind, and they do exist. But there is another kind, and I would say maybe even a larger fraction of people fall into this category, and I definitely do, is the collaborative researcher. They really play off each other's energy, and you come up with an idea, and then your student comes up with an even better one, and then you run it by your collaborator, and they have a different perspective, and they say, oh, well, you think it's secure, but hey, here's how I broke it. And, you go back and forth between different people. And I would say many of these results that we obtained were a result of this kind of a collaboration. We had a team here, we had a team at Stanford, my former postdoctoral advisor, a team at Urbana-Champaign. We had collaborators at Carnegie Mellon, we had collaborators at University of Southern California. All of us, in different projects, different configurations came together. And I would say it was like a little version of a Manhattan Project where, you have a goal, hey, there is this huge gap between what is possible and where we're at. And can we kind of figure out what are all the ideas that we can throw at it? And it was to us like, a kid in a candy store, because, we have all these tools and methods from this, long-standing area, right? Like 70-year-old area. And here's a new problem where nobody from this angle has ever really looked at it. And it was so much fun, and definitely the most fun I've had in my research career looking at any research problem.
So what you guys were doing was that you took that idea of, you took the current conception of what blockchain was, and you kind of broke that down to these first principles, as you call them, these basic ideas, and then tried to sort of redesign it from the ground up. Is that kind of what the process was like?
Yes, that indeed. So we would always ask, hey, if you did this, here is your algorithm, but we will say, hey, but the limits or the physical limits point that it could be even better. So we'll not stop it. We'll say, yeah, can you improve it more? Can you improve it more? And if somebody came up with something, hey, this is an improved version, then the others will say, hey, can I attack it? Is it really secure? Because, of course, you can get all the efficiency in the world if you gave up on security, right? Like, there's no use of such a system. So you want to have these. So that brings me to the trilemma. The trilemma is the three axes, really, that is required for a successful blockchain. The first axis is decentralization. So the algorithm should not have single points of centralization. Right? If you say, well, these are all the steps, they're done distributedly, but here's one step that can only be done by one node, right? Then you've centralized everything. So you should always look at points of centralization and try to make it as distributed as possible. So that's one axis, which is decentralization. Second is what we can call security, right? Security is essentially, is your algorithm secure? Which means even if some fraction of these, so now that you're building a distributed system, even if some fraction, and you're allowing anybody to really come and participate in the distributed system, even if some fraction of these people behave maliciously, your system should continue to function accurately. Your system security cannot depend on the assumption that everybody is going to follow whatever you tell them to do, because they're under no obligation, either moral or legal, to actually comply. And that actually provides a fascinating problem. And in fact, only with Bitcoin really we understood that it was possible to have both decentralization and security.
Mm-hmm.
And I would say this is a classical problem in a field called distributed computing, where people really have understood this kind of a question quite at its very fundamentals. But one paradigm shift that came with Bitcoin was in the earlier understanding. So here's what distributed computing wrangled with questions of this type, which said, suppose I have a program to execute on, and I have n servers. I have n servers, maybe 10 servers, and I know that two of them may misbehave in arbitrary ways, which I cannot control. Maybe they're malicious, maybe they have errors, we don't know what happened to them. But as long as 8 servers behave accurately, I need to make sure this computation is executed correctly. So this problem was called Byzantine fault tolerance or adversarial fault tolerance. So even if there are adversaries in the system, you need to be able to tolerate that. And this already had been deployed in many, many systems. For example, when you think of how you design sensors in an aircraft, you make sure that they have some kind of adversarial fault tolerance. Even if some sensors have been designed wrongly or malfunction arbitrarily, other sensors should be able to provide that information. And what this had already been studied and understood and so on. But what really Bitcoin brought up is, even in this system that I just said, in a distributed computing adversarial fault tolerance system, you needed to know that there were only n people, and out of those n people, only some fraction are malicious. But if you go into the real world and allow anybody to come into the system, I may have only my own personal MacBook, but I can create, if you just say, you have to create a user ID and you can participate in my system, I'll create 1 million user IDs, and it happens on Facebook, Twitter, and we know all of that, right? But especially if you said that as long as you control more than 50% of the number of nodes in the system, then you can take over the system. I'll just launch virtual machines and say, each of them run a separate program, and I'll just take over the entire network. And Bitcoin created a mechanism. This is called the Sybil attack. Sybil attack just means you create many virtual versions of yourself and then just go and take over a network. Mm-hmm. And to defend against Sybil attacks, Bitcoin created something called proof of work, which is each artist. So you can create as many entities as you want, but each of your power in the network is mediated by how much resource you have spent. In the Bitcoin case, you should have spent, compute power. So if I have a 1 gigabit machine, right, 1 gigabits per second machine, or 1 giga instructions per second machine, then I can only create so many entities. I cannot create, many more entities, and each of the entity will divide the resource, right? Yeah. So the total amount of power is not increased by creating many, many entities. So this is the defense against Sybil attack that created what we can call as public blockchains or public distributed systems. I think that is the shift between the classical field of distributed computing and blockchains. Is in classical field of distributed computing, you needed an authority to decide who are all the nodes that can participate in the system. And really that floodgate was opened with Bitcoin. And so anybody can come and participate in the system, and still you can build a secure system as long as a total fraction of resources controlled by honest users is more than 50% or whatever the number is. So that's really the basic paradigm shift enabled by Bitcoin, which created both decentralization and security, but it was lacking in the third axis of the trilemma, which is efficiency or scalability.
And that's where that entire thing we talked about came before, the 20 milliseconds versus 2 hours, and the few transactions per second versus millions of transactions per second. So what was your key insight, or I guess what would you say would be one of your biggest or most key insights in this entire process of redesigning blockchain that led to the results that you had, the results that you were able to actually very compellingly solve all these problems from the results that I saw at the talk you had? I don't recall the numbers off the top of my head, but it was like a huge difference. So what were your, I guess, most key insights in doing that?
The first thing that I said already, which is that our very different lens in looking at that problem helped significantly. So I'll say one thing here, which also pertains to the training and background in information theory and the more mathematical aspects of the problem, is there have been many attempts to actually get scalability. And a lot of people came up with many innovative methods. But the issue is, how do you show that a method that is scalable is also secure? And this is really, this requires a very sharp understanding of what it means by something is secure. Okay. So in fact, if you see in blockchains, a lot of creativity was unleashed by many people trying to create new algorithms, new methods, and so on, but without the corresponding guarantee that the algorithm is secure. And what happened is, the first thing that we did is we took up Bitcoin and kind of distilled out what it means for Bitcoin to be secure. And we could formulate that as a problem in random processes. So that's a kind of a leap, right? So you have a practical problem where people are using mining and other things, and what we could do is to distill out the essence of that problem as a mathematical problem in, if you think of a blockchain, there are blocks being built, and they could be built in a chain, but it could be a tree. And how does this tree evolve? And if you are an attacker, then you can control this tree to some extent. And we created very nice abstractions of this underlying process to distill out when is Bitcoin secure, for example, and obtain sharp understanding of, here are regimes. If the adversary controls so much fraction, then it is secure. If the adversary controls so much fraction, then it's not secure. So in information theory, these are called phase transitions. In a certain phase, it's definitely secure. In a certain phase, it is definitely insecure. And if there is a sharp boundary, the adversary controls more than 50%, then it is not secure. If the adversary controls less than 50%, then it's definitely secure. So we could understand these phase transitions. And once you understand why something is secure at that kind of a depth, then it makes it possible for you to alter the fundamental structure. And our core idea, at least in Bitcoin, was to say, or in one aspect of the problem, was to say that so now that we understand what makes it secure, can we understand what limits the scalability? Right? So you have these two axes, and anyway, we only consider the class of decentralized algorithms. So we're looking at these two axes and say, okay, now we know Bitcoin is secure, but what is really limiting its scalability? And that's a particular thing, which is the rate at which blocks were generated. And we had to look at the internal structure and say that if you can create many parallel versions of execution of this tree process, then you can speed everything up and still maintain the security without compromising it.
So in this three-pronged problem, basically, since you were able to understand or distill out kind of the security aspect to this neat mathematical form, or to this form that gave you a much stronger, more robust understanding of the problem. Once you had that, you were able to redesign even other aspects of the problem. Is that correct?
That's absolutely correct.
Right. Okay. So that's a kind of an interesting point. Instead of having to like deal with all of them one by one, it turns out that understanding one of them kind of enabled solving the other pieces of the problem as well.
Exactly. And because, the trilemma is a very tight rope to walk, because if you just leave security and just go to say, hey, I'm going to make it very scalable, then it's easy, but it's not useful. So what we did is we said, security, so we only consider decentralized algorithms. We first understand security. Now, without altering the security, how can I kind of improve on the scalability? Because now I understand precisely what contributes to the security of the system. So I will not tamper with it. Don't tamper with what's working, right?
Yeah.
Try to make different versions, parallel versions, whatever, that was really our thinking. Now that I know precisely, pinpoint what contributes to the security, don't touch that. But then you have room to play with other things. And then that's how you get the skill.
Yeah. I guess like if you have time for one last question for maybe a minute or two, would just be, well, what's happening next now that you guys have designed this entire thing? Like, what's going to happen next? It seems that has the problem been solved? Is it done now? Are we done? Like,
No, in research you've never done, and especially in problems of potential societal impact, like in blockchain, it's a long road. So we have some core understanding of some of the basic building blocks, but how do you take these building blocks and create systems? For example, how do you create a social network? It requires way more than what, just designing the rails. You have to design a train, you have to design the carriage, all kinds of things. And all of these require and have intricate interaction with the underlying rails. And so we're working on various problems. For example, one of the key problems is identity. Blockchains were created as an identity-free. One of the things in Bitcoin is it's an identity-free zone. Like, there's no requirement for you to have any previous identity to participate in Bitcoin. Mm-hmm. But that also creates a certain cost. In game theory, they say that there's a big difference between a one-time game and a repeated game. Right? So if you go and only interact with somebody one time, they can behave in very arbitrary ways. But if I'm going to see this guy again and again, they'll make sure they be a little nice to you. So it's the same thing here. So if we can add identity layer on top of Bitcoin or on blockchain in general, that can basically give you a huge leverage. So that's one example of what's interesting. How do you design incentives that make sure that these underlying scalable consensus mechanisms are also incentive compatible? So how can you make sure of all of that? How do you make sure that these tokens that are being generated, do they really have value? How do you understand the value of these tokens? So all of these lead to, I would say, more questions than what really, I would say it's only the starting point.
So in a manner of speaking, what you've done is you've made a much better engine, but you still need to make a better car, you still need to make a better airplane, you still need to make a better train. All of these different things need to be done. Okay.
Indeed. And you may want to customize your engine to these different things. You may want to make sure how they interact. And so that leads to a whole suite of fascinating problems.
Interesting. Cool. Well, I really enjoyed this talk. It was great. It was very, very interesting to me. It seems like we only scratched the surface here. There's a lot of other things that I guess we could have talked about. Maybe some other time we'll have time to do it. But I just want to thank you. I'm very grateful, and I learned a lot as well. And I hope the viewers and everyone who's listening to this will have also learned a lot and maybe gain some insight with some of the powerful ideas we've discussed.
Oh, yeah. Thank you so much. I think it was super fun chatting with you, and it's been a great pleasure. And thank you so much for hosting.